Good morning, students. Today we are going to discuss paper 6, unit 9, synthetic applications of organosilins. Synthetic applications of organosilins. The synthesis of organosilicon compounds when silicon tetrachloride uh, sil when reacting with the eth- ethyl magnesium bromide then gives diethylsilane dichloride. And some of the important silicon reagents are uh, trimethyl chloride, trimethyl iodide, trimethyl azide, and trimethyl triplettes. Applications of organosilins. First one is protection of functional groups. Trimethyl or trialkyl silane group is used as a protecting group for amine, no hydroxyl and carboxylic acid and terminal alkenes. Terminal alkenes. Terminal alkenes. When hydroxy groups reacting with the trimethyl chloride in presence of trialkyl and amine, then gives silyl ether is a product. When this primary amines reacting with the trimethyl chloride in presence of trialkyl and amine, trialkyl amine, then gives uh, alkyl silyl trimethyl is the product. Amino amino trimethyl product B formation takes place when when terminal alkanes reacting with methyl magnesium bromide then gives uh, um, alkyne alkyne magnesium bromide will be formation to express this alkyne magnesium bromide and reacting with the trimethyl trimethyl chloride then alkyl alkynyl alkynyl trimethyl product will be formation takes place when carboxylic acid reacting with the trimethyl chloride, then that is in presence of trialkyl aniline, then gives trimethyl carboxylate product will be formation takes place. So these are the protection of functional groups. So here also some examples are given. The protection of some uh, groups when here polyalkene by coupling reaction. So this is a polyalkenes by coupling reactions. So this is one of the method to synthesis of polyalkene polyalkenes by coupling reactions. So next we are going to discuss silyl enol ether and ketene esters. Yes, this is the so here uh, when trimethylphenyl enol ether are very important in organic synthesis. There are these are obtained by treatment of enolate anions with the trimethyl chloride. They are used to generate isomerically pure enolate ion in directed aldol condensation. B. For the formation of alpha substituted carbonyl compounds, specifically. C. In terminal and photochemical reactions. See the terminal and photochemical reactions. When silyl enol ether reacting with the aldehyde, silyl enol ether reacting with aldehyde, then that silyl enol ether source of the silyl enol ether is the source of alpha carbon anion. Silyl enol ether is the source of alpha carbon anion. This alpha carbon anion compounds reacting with aldehydes, then gives uh, beta hydroxy compounds, with carbonyl compounds will be formation takes place. So here addition will be takes place. So next another example here. So in case of this case of this cyclohexyl cyclohexene silylenol ether, when here this is more substituted more substituted enol double bond is there. This more substituted enol double bond reacting with benzaldehyde in pentaptite and tetrachloride in BCM, then that more substituted alpha carbon undergo reacting with the electrophilic carbon and carbon. In case of here, second example, in the second example, this silyl enol ether and the double bond will be formation takes place at less substitution side. This substitution side in silyl enol the double bond reacting with the electrophile centers, that less substituted double bond alpha carbon undergo reacting with electrophilic carbonyl carbon gives alcohols as the major product will be formation takes place. So the formation of this silyl ether double bond based on the base we have taken the base important. So in case of here, so we have taken to synthesis of silyl ether when here 2-methyl cyclohexanone 2-methyl cyclohexanone. So when in this 2-methyl cyclohexanone reacting with the trimethyl silyl chloride in presence of tri triethylamine DMF triethylamine DMF, then gives more substituted silyl ether double bond will be major. In case of this 2-methyl cyclohexanone reacting with lead tetraestate, then gives less substituted silyl ether double bond is the major product will be formation takes place. This is a base purely based on the size of the base we have taken. Here trimethyl amine is the small size base, therefore abstract the proton from more alpha carbon position, resulting silyl ether double bond is stable. When in case of the tetraestrate is a bulky base, subtract the proton from less substrate alpha carbon, then corresponding product will be major will be formation takes place. So here also one example we have take discussion here. So next one example, ethyl carboxylate. This ethyl carboxylate reacting with lead lithium diisopropylamide, then in presence of tetrahydrofuran, then triethyl silyl chloride. Then the product is ketene ester will be formation takes place. Ketene ester will be formation takes place. Next one is synthetic applications of trimethyl silyl ether and their ketene esters. Synthetic applications of trimethyl silyl ether. Synthetic applications of trimethyl silyl ether and and ketene ester. Trimethyl silyl enol ether and ketene esters undergo variety of synthetically useful reactions. Some of the very important reactions are there are many used for generation of specific enolate ions from unsymmetrical ketones. Second one is they are used as a carbon nucleophile. First application is alpha alkylation. When here we are taken this silyl ether, when this silyl ether reacting with the uh, methyl lithium, then the product will be formation takes place when the corresponding product undergo reacting with the benzyl bromide, then benzylation takes place at the mole substitution of silane ether. That is a major product will be formation takes place. And here also another example is there. In this another example here when silane ether reacting with silane ether reacting with the tertiary butyl chloride, When this tertiary butyl chloride, then in presence of titanium tetrachloride, then that alpha position under electrophilic substitution takes place. So here are also some examples are there. When in this case, so in this one this ester reacting with the triethylamine in presence of trimethylsilyl chloride, then then we are getting ketone. Then between ketene ester will be formation takes place. This ketene ester reacting with the alpha beta unsaturated carbonyl carbon, then undergo uh, 1,4 addition takes place. Next, synthetic applications of iodo trimethylsilanes or trimethylsilyl iodide. When this trimethylsilyl chloride reacting with the sodium iodide, trimethylsilyl chloride reacting with sodium iodide, then gives trimethylsilyl iodide, which the product will be formation takes place. This trimethylsilyl iodide is the source of uh, in this in this carbon in this compound. Next undergo applications are dialkyl dealkylation reaction. Dealkylation reaction. When this dealkylation reactions, when that this ester reacting with the dealkylation reaction, when here this ether in this case the ether reacting with the trimethylsilyl iodide in presence of sulfonal, uh, then in presence of water, that ether undergo elimination of alkyl group, then converted into ketone amide will be formation takes place. Next, formation of iodo compounds. Formation of iodo compounds. Reaction of cyclic ester with iodo-trimethylsilane gives iodo-carboxylic acid. Iodo-carboxylic acid product will be formation takes place. So in this lactone reacting with trimethylsilyl chloride in presence of sodium iodide, then estronitrile followed by hydrolysis, then gives halo compounds will be formation takes place. Opening of the ring takes place. Then carboxylic acid and iodocarboxylic acid will be formation takes place. Reaction with the alpha beta unsaturated carbonyl compound. In this reaction with alpha beta unsaturated carbonyl compounds, so trimethylsilyl, when this alpha beta unsaturated carbonyl carbon reacting with the trimethylsilane, trimethylsilyl iodide, iodine attacking at the beta position, then forms silyl enol ether will be formation takes place. The silyl enol ether reacting with the acid proton, then alpha carbon convert it to attacking at hydrogen, then carbonyl compound retain takes place. Next one is reaction with the next one is reaction with alpha beta cyclopropane ketone. Next one is reaction with alpha beta cyclopropane ketone. In this alpha beta cyclopropane ketone, when reacting with trimethylsilyl iodide, when reacting trimethylsilyl iodide, trimethylsilyl iodide, then this iodine attack at cyclopropane carbon atom, bridges that cyclopropane carbon atom, attacking cyclopropane carbon atom, then this bond shifting to formation of double enolate, the another bond shifting to formation of enolate. This then resulting product is silyl ether will be formation takes place. This silyl ether is reacting with the proton source, that is a water molecule, then gives that iodo ketone will be formation takes place. Next, alcohols to reaction with alcohols. and alcohols are converted into iodo compounds. When trimethyl iodide reacting with alcohols, when trimethyl iodide reacting with alcohols, elimination of hydroxy group takes place. In the place of hydroxy group, all the iodine is substitution will be takes place. Next one is reactions involving in silicone stabilized carbon anion. Reactions involved in silicon stabilizer carbon. Silica stabilizes alpha carbon anion. Silica stabilizes alpha carbon anion and beta carbocation. Silica stabilizes the alpha carbon anion and beta carbocation. So now in this we are discussing Peterson alkane synthesis. In this Peterson alkane synthesis, when alpha silyl carbon anion, alpha silyl carbon anion reacting with carbonyl compounds, then gives beta hydroxysilanes are the products. This beta hydroxysilanes undergo elimination gives alkenes are the product will be formation takes place. Next reaction with the vinyl silanes. Reaction with the vinyl silanes. Reaction with vinyl silanes. These vinyl silanes reacting with electrophiles. These vinyl silanes reacting with electrophiles then gives electrophile attacking at alpha position. Then beta position is a positive charge will be developed. Therefore, therefore, uh, therefore, we know already silica stabilizes alpha carbon and beta carbocation. So yes, with respect to silica, beta carbocation will be formation takes place. It is stable when attacking with the nucleophile. The bond between alpha carbon and silica is shifting to formation of double bond with at positive charged position. Therefore, we are getting alkenes in the product. That means silica position is substituted by the electrophile. Silica position is substitution by the electrophile. Next one is reacting with acid halides. When vinyl silanes reacting with acid halides, when vinyl silanes reacting with acid halides, we know already electrophile is substituted by the silica position. When this vinyl silanes reacting with acid halides, in this acid halides, SL is the electrophile group. SL is the electrophile group. CH3C double bond positive. So this SL is substituted by the silica position. This SL is the substituted by the silica position. Next, conversion of alkynyl silanes to or vinyl silanes to carbonyl compounds. Next one is conversion of vinyl silanes to carbonyl compounds. When this vinyl silanes, when this vinyl silanes undergo epoxidation with metachloropropylenoic acid, epoxidation will be formation takes place. The double bond undergo epoxidation takes place. This epoxidation group and the reacting with the methanol, the reacting with the methanol in presence of acid medium, methanol acid medium, then gives carbonyl compound is the major product will be formation takes place. Here also some example is there. So next one is one is Nazarov cyclation. Next one is Nazarov cyclation. That is reaction of alpha beta unsaturated SL halide. Reaction of alpha beta unsaturated SL halides um, with with vinyl silanes. Vinyl silanes in presence of Lewis acid catalyzed. Initially, they forms a uh, diene dienone will be formation takes place. Dienone will be formation takes place. That means when alpha beta unsaturated SL halides reacting with vinyl silanes, then in presence of Lewis acid, then forms dienone will be formation takes place. This dienone reaction with the with the Lewis acid, then undergo cyclation takes place. The double bond is migrated towards formation of enolate, formation of enolate intermediate, like intermediate, then forms a secondary carbocation. This secondary carbocation, the secondary carbocation will be formation takes place. This secondary carbocation undergo migration of the conjugated double bonds takes place, then forms tertiary carbocation. This tertiary carbocation involved in the loss of proton, then gives and then followed by hydrolysis, then gives cyclopentanone. Is the product will be formation takes place. So what is the nature of cyclation is dienone. Dienone is converted to cyclopentanone. Is the nature of cyclation. Dienone is converted to cyclopentanone. Is the nature of cyclization. Next, reaction involving allyl silanes. Reaction involving in allyl silanes. Allyl silanes. When these allyl silanes reacting with electrophile, when allyl silanes reacting with electrophile attacking at terminal alkene carbon, then beta carbon silanes, beta carbocation silanes will be formation takes place. This beta carbocation silanes reacting with nucleophile. This beta carbocation silanes reacting with the nucleophile then forms allyl electrophile attached allyl group will be formation takes place. That means shifting of Chilean and electrophile will be takes place. So here one example is there. Here alpha beta unsaturated SL chloride reacting with the allyl silanes. So this SL chloride gives SL carbocation. This SL carbocation uh, attacking at gamma position of LL silane carbon, gamma position of LL silane carbon. Then this then gives be- beta carbocation with respect to silicon silanes. The beta carbocation with respect to silanes. This beta carbocation silanes, beta carbocation silanes reacting with nucleophile. The bond between carbon and silica shifting towards beta carbocation and alpha carbon. That involves formation of double bond between uh, takes place. And fluoride, reaction with the fluoride induced reactions of silanes. Reaction with the fluoride induced reactions of silanes. reaction with the fluoride, induced reactions of silanes. When allyl silanes reacting with the uh, ammonium fluoride reacting with the trialkyl ammonium fluoride that involves in the elimination of trimethyl silyl fluoride, then allyl carbocation, allyl carbon anion will be formation takes place. This allyl carbon anion reacting with the electrophilic center. Here we are taken diphenyl ketone. We have taken diphenyl ketone. This ketone react diphenyl ketone that allyl carbon anion attacking at the carbonyl carbon of diphenyl ketone, then gives alcohols is the product will be formation takes place. So another example here, alkylation of another example for alpha alkylation with benzyl bromide in presence of tetra alkyl ammonium fluoride in presence of tetrahydrofuran. So that alkylation takes place at less substitution side of alpha carbon of carbonyl carbon is a major product. That is cis trans is the major product. Cis is the minor product. Will be formation takes place. Next reaction with the terminal trimethyl cyanide. Reaction with the trimethyl cyanide. When this in case of trimethyl cyanide, the in generally when carbonyl compounds reacting with the cyanocatalyzed, when reacting with CN minus reacting with carbonyl carbon, then give um, alpha cyano hydroxide anion will be formation takes place. This hydroxide anion reacting with the trimethyl cyanide, then gives alpha, then gives silyl cyano um, alpha cyano trimethyl silyl will be formation takes place. Yes, in this compound, aldehyde reacting with trimethyl cyanide in presence of CN catalyst, CN minus catalyst, then gives that the carbonyl carbon attached to CN and O CI trial O-silyl trimethyl will be there. It is undergo hydrolysis, then gives cyanohydrines are the product will be formation take. This cyanohydrine undergo hydrolysis, then gives hydroxy acids are the formation takes place. And when this compound cyanohydrines reacting with lithium aluminum hydride, that cyano is converted to amine takes place when reacting with lead lithium diisopropylamide that silyls cyano attached carbon proton abstract with the base, then gives negative charge. This negative charge is stabilized by benzene ring and cyano group. So it is a stable negative charge at that position. This negative charge reacting with any electrophilic center, I am taken phenyl methyl ketone carbonyl compound attached to this carbonyl compound gives corresponding alcohol is a major product will be formation takes place. Next, protecting groups in organic chemistry. Protecting groups in organic chemistry. Here, we are taking one compound. In this compound, next unit is unit 10, protecting groups in organic chemistry. So in this compound, one example here, I am explaining protecting group concept. So in this compound, when in this compound, we have two functional groups are there, carbonyl carbon and ester who are there. ketone and ester group is there. When this compound reacting with lithium aluminum hydrate, in presence of ether, both ester and carbonyl compound undergo reduction takes place. Both ester and carbonyl compounds undergo reduction takes place. So, but I want to reduce the carbonyl carbon. I want to reduce the, I want to reduce the, so I want to reduce the ester. I want to reduce the ester. Mm, I want to reduce the ester. So I then ketone is as it is. So in this case, in this my condition, so when see in this compound, ketone and ester as there, both the compounds when this compound react subjected to lithium aluminum reduction, both acid and ester undergo reduction takes place, converted into hydroxy groups. But I want to reduce ester, but ketone is as it is remain in the product. So for this case, so first I am protected the I am reacting with the glycol. I am reacting with this compound with glycol in presence of acid medium. So that carbonyl compounds undergo the carbonyl compounds undergo protecting as a ketol. The carbonyl compound undergo protecting as a ketol, and ester is as it is there. When this compound reacting with ketol ester, reacting with the lithium aluminum hydrate, this lithium aluminum hydrate reduces the ester into alcohol, esters into alcohol, and that ketol is does not affected. That either does not reacting with the lithium aluminum hydrate. Only esters are reacting undergo reacting with the lithium aluminum nitrate, then gives alcohols. So these hydroxy ketol is it. This hydroxy ketol undergo hydrolysis, then gives uh, then gives ketone as ketone alcohols will be formation takes place. This is a protecting group. The protecting group, the group which is temporarily inactivate the functional groups, then the groups are called protecting groups. The groups which are temporarily uh, inactivate the function group, then the groups are called protecting groups. So no protection of alcohols. So protection of alcohols, uh, protection of alcohols as the ether and ester protecting groups. Ether and ester protecting groups. When alcohols reacting with the base sodium hydrate, followed by reacting with methyl hydrate, then gives methyl ether will be formation takes place, and also phenol reacting with the base and methane, phenyl aryl ether will be formation takes place. So some another example also there. Then alcohols reacting with dimethyl DMSO, dimethyl, dimethyl sulfate, DMSO. Then protection of alcohol this will be takes place. Next, benzyl ether protection as a benzyl ether. So alcohols reacting with benzyl halides. So that in presence of base, that benzyl loss of HX, then benzyl ether will be formation takes place. Tertiary butyl ether. When this alcohols reacting with the alcohols reacting with the 1,1 dimethyl or 2-methyl 2-methyl propene, when reacting 2-methyl propene. So that is gives tertiary butyl ether will be formation takes place. These ethers are deprotecting with the TFA or TFA or TFA trifluoric acid or trimethyl then ethers are retained as alcohols. Next, So tetrahydro tetrahydropyrenyl ether. Tetrahydropyrenyl ether. When this tetrahydropyrenyl ether is a ether provide to be one of the very important protecting group in organic synthesis. It is a cyclic ester and is obtained when alcohols reacting with dihydropyrene. When this dihydropyrene reacting with alcohols in presence of acid medium, then gives tetrahydropyrene is the product. Tetrahydropyrenyl ether will be formation takes place. Tetrahydropyrenyl tetrahydropyrenyl ether will be formation takes place. So here also when alcohols reacting with the tetrahydropyrene, then dihydropyrene gives tetrahydropyrene is the product will be formation takes place. Next one is trimethyl ether. Then next one is trimethyl ether. So when alcohols reacting with trimethyl halide, then this trimethyl ether will be formation takes place. Then cleavage of this next cleavage of uh, trimethyl ether in presence of KF and aqueous aqueous ethanol. Then alcohols will be formation takes place. Next one is ester protecting groups. Next one is ester protecting groups. First, ester protecting group. First one is ester protecting groups. When alcohols reacting with acetic anhydride, then forms estate is the product will be formation takes place. Or alcohols reacting with SL chloride, then forms estate is the product will be formation takes place. And benzoates, when alcohol reacting with the benzyl chloride, benzoates is the product. And when these benzoates are undergo base hydrolysis, then gives alcohols are the products. The benzoates undergo sulfonification is called alcohols are the product will be retained. Next, protection of diols. When 1,2 diols are reacting with estone, then forms cyclic estol or ketol will be formation takes place. In case of estone, cyclic estol will be formation takes place. So deproduction of this cyclic estol with the acid medium, then 1,2 diols are the return takes place. Next, protection of aldehydes and ketones. When aldehydes reacting with methanol, then gives dimethyl ester is the product. When alcohols reacting with then carbonyls reacting with glycols, then gives cyclic estol is the product. Cyclic ketols are the product. If aldehyde is estol, ketone is ketol is the product. When this estol and ketols are under acid medium, then carbonyl compound is the retained takes place. Next, dithioketal and dithioester protecting groups. When carbonyl compounds reacting with thiomethanol gives dimethyl ester. When carbonyl compounds reacting with thiomethanol gives dithioketal or dithioesters are the products will be formation takes place. When this In this dithioestol or dithioketals under reacting with the acid medium, then carbonyl compounds are retained takes place. Protection of amines. When this protection of amines, N-alkyl or N-silyl protecting groups. N-alkyl or N-silyl protecting groups and primary amines reacting with the benzyl halides in presence of base, then gives secondary amines of the product will be formation takes place. This secondary amines, this benzyl alkyl amines undergo reaction with the hydrogen palladium, then primary amines of the product will be formation takes place. MSL protecting groups. MSL protecting groups when reacting with prime NSL protecting groups when primary amines reacting with acetic anhydride or SL chloride, then NSL protecting group NSL group will be formation takes place. Then this NSL group undergo acidic condition. Then again amine group it return takes place, and protection as a N-benzoyl protecting group when primary amine reacting with benzoyl chloride in presence of this, then this gives N-benzoyl group protecting group. Then deprotection of this N-benzoyl protecting group is in presence of acid medium, then gives primary amines of the product will be formation takes place. Next one is N-carbamate protecting group. N bark bark N bark, and it is primary amines reacting with the that is esters, then gives N-bark will be formation takes place. N benzoyl gives benzoyl that's NCBZ will be formation takes place. This N-bark and NBCBZ will be formation takes place. N-bark and NCBZ will be formation takes place. This bark and CBZ are the deprotection by hydrogen palladium. It takes place.